So this is Engineering 221. I am Dr. Matthew Hartman. My office is over in Nefkin Hall, room 211. For those of you that are not aware of where Nefkin Hall is, it is the building that is catty corner with the IESB. So if you go out the main doors, it's the one that you're looking at that's diagonally across the street. My office hours are Tuesday through Friday, 2 p.m. to 4:30 p.m. I do want to make you aware of something here. Ada Kappa Nu, the Electrical Engineering Honor Society, holds tutoring, circuit tutoring from 3:30 to 4:30 p.m. on Tuesdays and Thursdays in Nefkin Hall, room 120. As I am the faculty advisor of this organization, I usually also participate in these circuit tutoring sessions, which means from 3:30 to 4:30 p.m. during my office hours, I won't actually be in my office. I'll be downstairs in Nefkin helping students with circuits questions and all of that kind of good stuff. Just wanted to make you aware of it. Just as another thing here, IEEE, the Institute for Electrical and Electronics Engineers, which I am also the faculty advisor for, has tutoring sessions Mondays at 7 in IESB 224. I do not show up for them because I live in Minden and they don't pay me enough to make me stay here after 5 p.m. on most days. So anyway. So emergency classes. Oh, actually, my email address is just my last name at latech.edu. There's the phone number for my office. Good luck. Emails are better, or just hunting me down during my office hours are best. So emergency class disruption policy, in the event of any extreme weather events or another global pandemic, who the hell knows? We will continue the class via Canvas and Zoom. I will be on Zoom during every single class meeting. I use Zoom to record all of my lectures, and then I post those lectures to my shitty YouTube channel, as well as our Canvas page and all of that kind of good stuff. So you guys should have access to all of this. Just as another tangent, on my shitty YouTube page, I have recordings from every circuits class I've taught since we had to start using Zoom when COVID began, I think in the spring of 2020. So there's like several years worth of old lecture videos and all of that kind of stuff on there if you want to peruse them for whatever reason. The only thing that really changes quarter to quarter is example problems, because I usually just make them up as I go. So anyway, just making you aware of that. Let's see, course objectives. To put it very, very succinctly, we are going to learn a whole hell of a lot about how to analyze circuits in this class. Not only DC circuits, but also circuits undergoing transition between two different DC steady states, as well as sinusoidally excited circuits. So lots and lots of circuit analysis going to go on in this class. The official textbook for this course is Engineering Circuit Analysis 10th edition by Height, Kemmerly, Phillips, and Durbin. While this is a perfectly good book, I don't think any of you actually need to purchase it, which is why I don't put it as a required purchase. It's only recommended. If you really feel the need for a circuits textbook, I would highly suggest that you hop on Google and you type in the following words. ULABY, that's Ulabi. It's a electrical engineering professor out of the University of Michigan's last name, and then CAD. The first link here is for a free textbook called Circuit Analysis and Design. These guys allow you to download this textbook entirely for free. A hard copy of the book, I think they charge you 75 bucks for to get it shipped down here. But essentially, you can download this free textbook instead of stealing someone else's intellectual property, because we all know textbooks are rampant on the internet. These guys are literally giving it away. And in my opinion, it is a rather good book. So if you were going to go out of your way to find a circuits textbook to supplement this class, this is a good one to use. Let's see. Disability disclosure. Anybody that needs testing or classroom accommodations based on a disability need to discuss those with me as soon as possible. I have already scheduled an extended time room for exams 1, 2, and 3 for this class. I would highly encourage you, if you have a diagnosed learning need that would allow you to use those extended time rooms, I highly encourage you to go ahead and sign up for that. I have had students in the past who wanted to take their first exam and just kind of see how it went before they went through the TDS process. To me, that is wildly dumb. If I had the opportunity to be in a quiet room without 100 people shuffling around, making noise, coughing, sneezing, belching, etc., I would absolutely do it. So I highly encourage anybody who has this as an availability to just go ahead and sign up for it. All right, so class attendance policy, the official policy is up here. It's governed by policy 2206. There's a link if you want to read it. Essentially, it says something to the effect of you can only miss 3 class days and all that kind of good stuff. Now, that is the official policy. The unofficial policy is you're paying to be here. So if you don't want to be here, I'm going to get paid either way. You do you. The videos and all that kind of stuff will be available on Canvas and YouTube. There will be a small form of punishment for not physically showing up to class and all of that kind of good stuff. We'll talk about that here in a minute. But realistically, it would only impact you by roughly half a letter grade. So if you feel that your time would be better served sleeping in and then watching the videos on YouTube or whatever, that is your choice. You are adults. Honor code, essentially the same stuff you've been putting on your papers. For your homeworks and all that kind of stuff. Being a student of higher standards, you pledge to embody the principles of academic integrity. And then there's some definitions here regarding policies for academic misconduct, specifically regarding behavior and cheating. You can read those at your leisure. For behavior, my usual spiel is if you're less of an asshole than I am, you're doing great. And for cheating, don't do it. That really, really pisses me off, and I have no issues whatsoever with sending you up for an honor code violation. All right. Homework. So homeworks in this class will be handled using web work. I don't know how many of you have had the opportunity to deal with web work in the last couple of quarters, but there have been some changes made. So if we tab over here to just the general Canvas page for our course, and I would encourage all of you to do this. Right below the introduction module, there's one for homework assignments, and then it has the web work launcher. So if you click on this launcher thing and then tell it to load web work in a new window, it should automatically log you into web work and assign assign you to all of the individual assignments in this course. There will be 24 homework assignments in this class. They are all weighted equally. So some of them have 3 problems, some of them have 7 problems. They're all the same weight as far as I am concerned. The way that web work calculates your grade is it takes your total number of points that you've scored across all assignments and divides it by the total number of points available. That is not how I will be weighting your grades, right? Every individual assignment will be worth the same amount. So you can use this tool to tell you how you did on an individual assignment, but I'm telling you explicitly, if you scroll down to the bottom and look at your course total for the homework, you are going to have a different number than me unless the number is 100% or 0%, okay? So just so that you're aware of that. The first homework assignment in this class will not be assigned until Friday's class meeting. So how I have these homework assignments set up is that homeworks will be due midnight of the following class meeting. So what that means is for the assignment that is assigned to you all on on Friday, it will be due on Monday at midnight. You will have 2 additional days, so up until Wednesday at midnight, where you can receive 75% of the total credit. So I am encouraging you, if you want to receive full credit, you need to stay on top of your homeworks in this class. The reason why I am pushing you very, very hard is because it is very easy to fall behind and just get wrecked by the tests if you fall behind, okay? So I know you're probably thinking I'm a dick. You're not wrong, but it is very important for you to keep up with your homeworks in this class if you do not want to just get utterly destroyed by the time the test comes around. So they're due midnight of the following class meeting, and then there's a 2-day grace period where you can still receive up to 75% of the total credit, okay? So this is a little different than I've done in previous quarters. Previous quarters, the homework was due the day after the next class meeting, and then you had one day at 50%. Now it's due the next class or the midnight of the next class meeting. You have 2 days at 75%. So realistically, I would expect to see homework scores actually trend up due to this change. Just want to let you know why I did it and all that kind of good stuff. All right, mini labs. So there are 8 miniature lab exercises in this class, the first of which will be held this Friday. Okay. So there is a kit for this class. It costs a whopping $10, and realistically, only one person per table really needs to purchase this kit, or you guys can all shell in, $2 to $2.50 a piece to buy the kit. It's got some resistors, capacitors, inductors, things like that. It's got an extra breadboard and all that kind of jazz. So whoever you think is the least likely to drop the class, have them be the keeper of the kit. Try to make the cost not super prohibitive for you guys and all that kind of stuff. So it's only $10, but there is a purchase required for this class. All right. Exams. So there are going to be 3 exams given during this course. The first exam, and I have a schedule here we'll look at in a couple of minutes, is largely over DC circuit analysis techniques. The second exam is over some more advanced DC circuit analysis techniques and transient analysis, as well as capacitors and inductors. And then the third exam is on steady state sinusoidal circuit analysis and operational amplifiers. I have already put exam review materials up on our Canvas page. You have access to the review materials for exam 1, exam 2, and exam 3 already. I'm going to say this now. I would like for you to write it down. It will be recorded. Exam 3 is not cumulative. So we made a switch to non-cumulative exams within the last year or two. The old exams that I give you guys access to, for the most part, are cumulative exams. So I'm telling you very explicitly, there is one exam 3 that says non-cumulative. That's kind of your for sure study from this. And then let's say the last third of the other ones, the old cumulative exams, you can also use that as extra practice. So there's more exam 3s available than the other ones because they are not the correct modality. All right. So just to reiterate, exam 3, very much not cumulative. All right. So when you're taking your exams, you can only use FE approved calculators. So you can find the list at the link there. FE approved calculators include the TI-30X. How many of you guys have a TI-30X? Great. You're going to want to, I don't know, throw away, burn, whatever. Just replace that shitty peasant calculator at your earliest convenience. The TI-30X will technically work for this class, but you will not have a good time with it at all. We're going to be solving lots of systems of equations and things like that. We're going to be dealing with complex numbers, and that calculator is not the best at handling those type of things. So my personal favorite calculator for this class is the TI-36X. I like this calculator a lot because it can solve 3 equation, 3 unknown systems. It can also do all of the complex math that we're going to be doing in this course. And you don't have to switch the mode of the calculator to go back and forth between solving systems, performing simple calculations, and dealing with complex numbers like you have to do for the Casios. Okay. Speaking of Casios, the Casio calculators that are FE approved are the Casio 115. This guy is essentially the exact same thing as the TI-36X as far as functionality goes. But in order to use the system solver, you have to switch to a different mode. In order to handle complex numbers, you have to switch to a different mode, etc. I find that to be a pain in the ass. So I have one and I learned how to use it because a lot of you guys have them, but it is not my preferred calculator. Then we also have the Casio 991. This one has been discontinued. There is a newer version of it that is black. I'm not as familiar with it because it has a slightly different button layout, but it's largely the same thing. This is the only FE approved calculator that can solve a system of 4 equations and 4 unknowns. So it is slightly more powerful than the others. Like I said, this white version like this has been discontinued. You can find some counterfeits on eBay. Do not buy them. They are hot garbage. They just give you constant math errors. I've had students buy one off of eBay, buy a quote unquote new one off of eBay for like 50 bucks, which these were like $22 when they were real Casios, and then fail the shit out of my test, not because they didn't know what they were doing, but because their calculator literally could not perform the simple math operations because it was a knockoff. So the newer 991s are all black. Make sure that you buy it new. Any used Casio 991, I would be very, very wary of, just because I'm surprised there's a huge market for counterfeit calculators, but apparently there is. So. Also, the HP 33S is an FE approved calculator, but HP calculators use some fancy witchcraft order of operations that I don't understand, so I'm not going to buy one and I'm never going to learn how to use it. I've only had like 3 students that in the 7 years I've been teaching this class have an HP, so that's your bag of cats if you choose to go that route. So I personally would go for the TI-36X or the Casio 115 or the 991. HPs, if that's your bag of cats, great. TI-30 is a shit peasant calculator and it will ruin you in this class. I'm just being very, very blunt about it. Okay. Should be fairly obvious, but you can't use your cell phones during the tests. All right, so grade breakdown for this class. The homeworks are 15% of your grade. In-class assignments, I've passed one of these out to you all, are 5% of your grade. So these in-class assignments, they are not graded for completeness or correctness. They are essentially a participation grade. I'm doing them a little bit differently this quarter than I have done in the past because I've just had students turning in blank forms, expecting to get no credit, and students have been just turning them in digitally and not bothering to show up to class and all that kind of stuff. So to combat that, you are going to turn in your physical copies to me at the end of every class meeting. That's how you're going to receive credit for doing them. So if you're not here, then obviously you couldn't do the in-class assignment and you don't get that participation grade for that day. Okay. So this is a kind of a secondary way to check roll. And if you want to receive this half a letter grade of credit, you need to physically be here and working on them instead of watching soccer or some such nonsense on your phone. Mini labs are worth 5%. There is a mini lab makeup day at the very end of the quarter. So if you have to miss a mini lab due to illness, athletic competition, or something like that. By the way, I think your wallet fell on the ground. Yeah, okay. But anyway, if you have to miss a mini lab, there is a day dedicated to making up mini labs at the end of the quarter. So don't harass me. It's literally on the syllabus. Show up on that last day to make up any mini labs you missed, and you're good to go. Then we have our 3 exams, exams 1, 2, and 3. Each of them are worth 30% of your grade, and you notice there's some fancy symbol there. That fancy symbol has a little footnote here saying that the weight of the exam on which you receive your lowest score will be reduced to 15%. So effectively, you can have one bad test day in this class, and as long as you don't make less than a 33, it's still possible for you to make an A in the course because that lowest test grade is scaled down so heavily. If you have 2 bad test grades, you're kind of SOL. So this is me acknowledging that everybody can have a bad day, and sometimes they will occur on a test days, but if you're consistently doing poorly on the test, you are not going to pass this class. Yes, sir. No, so the others will stay at 30. It's just the one that you do poorly on, or have the lowest score on, gets reduced to 15. So if we look at this, 15% for homeworks, plus 5% for ICAs, plus 5% for mini labs is 25% total. Then we have 2 exams at 30% and another exam at 15%, makes 75. 25 plus 75 comes out to be the regular 100%. So no increase in weights, just the one you score the worst on gets knocked down to help you out a little. For what it's worth, I firmly believe that the first exam in this class is the hardest one by far. Okay? I say that because we cover so much material. We have 8 different lecture topics that are going to show up on that first exam. And while they are related to each other, they are largely independent of each other. And so I'm expecting you to do a lot of different things. That is rather difficult. The second exam is really only over Thevenin and Norton equivalent circuits, inductance and capacitance, and transient analysis. So it's 3 topics that we spend roughly 7 to 8 class meetings over. That's the easiest exam. Third exam is somewhere in the middle. It's largely what we are doing on exam 1, except we're using complex numbers, and then there's some new power relationships towards the end. So in order of difficulty to me, it's exam 1 is hardest, exam 3 is the middle, and exam 2 is the easiest. You guys can take my word for it, or you'll find out hopefully here in the next several weeks. All right, so the grading scale for this class is a standard 10-point scale. I'm a bit of a stickler. I don't like rounding or curving or anything like that. So if you want to make an A in this class, your grade needs to exceed 90%. Just for what it's worth on an exam, and you'll see this when you look at some of the practice exams, there are times where I make mistakes. If I make a mistake on an exam or something like that, I throw the question out and everybody gets credit. Additionally, there is 10 points of bonus credit available on each of the exams as well, intentionally. So we've got essentially a letter grade worth of participation from the in-class assignments and the mini labs. There's, I think it comes out to be in the ballpark of 5 to 6% towards your final grade available in bonus from doing extremely well on the exams. So I think that's a reasonable thing to give you guys, and then say, hey, I'm not going to curve because I don't think it's necessary. So anyway, that's my grading policy. Let's see. Syllabus changes. I don't expect the contents of the syllabus to change, but I retain the right to do so. If I do change the syllabus, I will let you know. For what it's worth, this usually doesn't happen. Last quarter, I had to change the syllabus because we missed a day because of supposedly bad winter weather that didn't actually exist, and so I had to reschedule some things. That's the kind of changes I would expect to see. More stuff about the emergency notification system. COVID-19 policy, essentially, don't show up if you're sick. If you get me sick, I've already had COVID and strep this winter. I will be furious if I come up with flu or RSV, just as a heads up. Counseling services are available to you at no charge. You can schedule all of that kind of stuff at this portal here. And then we have our tentative course schedule. I already have the exam dates and all of that kind of stuff set on here. So your first exam will be April 7th at 6 p.m. in IESB 318. I've already reserved the room. Second exam, April 28th. And then your final exam is May 21st. May 21st is the Wednesday after senior grades are due. So if you are a graduating senior, you need to let me know as soon as possible, and then you will take your exam Tuesday during the day so that I can get it graded before your grades are due that afternoon. And then, as I mentioned previously, there is a mini lab makeup day that is the last day of the quarter. So if you miss a mini lab for any reason, you're welcome to come and make up that mini lab at that time. Any questions regarding the syllabus? All righty. So we are now going to get into our lecture for today. So today we're going to be talking about basic circuits terminology. So nothing particularly math heavy or at all today. So the reason why I'm taking time to devote a whole lecture to you guys understanding basic circuits terminology is because you all had different people teaching you the Engineering 120 series and stuff like that. And so I want us to all have a common language to use when we're describing what's happening in a circuit and all of that kind of good stuff. Okay. So the first thing that I'm going to do is I'm going to introduce a generic circuit element, okay? So I'm just going to put a terminal here and a terminal down here. And then between these two terminals, I'm going to have just a box. And this box represents a generic circuit element. We don't know what this particular circuit element is, but we can see that it is a two-terminal circuit element because there's two leads coming off it, okay? So this could be a battery, it could be a resistor, a capacitor, inductor. It wouldn't be a transistor because transistors typically have 3 or 4 terminals. It wouldn't be an op amp because those guys can have as many as 8 terminals. So this is just a generic two-terminal circuit element. Generally speaking, I will label these generic circuit elements with some kind of identifier. So this guy is going to be circuit element A, okay? So these two terminals, which I'm going to circle here in orange for right now, are how we connect this generic circuit element to other things, like other circuit elements, sections of wire, etc. Okay. The majority of the circuit elements that we're going to be dealing with in this class are two-terminal elements like this guy. The only element that we're going to deal with that has more than 2 terminals is the operational amplifier, which I mentioned can have as many as 8 terminals. And we'll talk about those 8 terminals and what they do and what role they play when we get to op amps more towards the end of the quarter. So if I were to connect another circuit element, so let's be really unimaginative here and call it a circuit element B, I will form what's known as a network, okay? So we are going to define a network as a system containing 2 or more circuit elements that are connected together. By the way, my penmanship gets too shitty and unreadable for you guys. Please let me know and I will happily erase it and write it better. Okay. So we have now a simple network that is containing 2 circuit elements. Okay. Another thing that this network is containing is what we're going to call a node, where a node is going to be a point of interconnection. And I'm going to put point in parentheses, and we'll see why in a moment. There's quotation marks of interconnection between 2 or more circuit elements. So before we identify our nodes or anything like that, I'm going to make this network a little bit more difficult or a little bit more robust by adding a few more circuit elements, okay? So I might add a circuit element C that is connected between elements. So on one side, it's going to be connected to element B. On the other side, it's going to be connected to element A. And then I might have an element D over here on the right-hand side, like so as well, okay? So those little circles that I've been drawing, and I won't draw them consistently because we won't really need them, I'm just trying to explain things here, are representing where the terminals essentially terminate for each of these elements, okay? So we are considering a node to be a point of interconnection between 2 or more circuit elements. So I might choose to represent this guy right here has a node, which I've just colored it in as red. This guy over here might be a node, which I'm going to color it in as blue. And then this guy down here might be a node, which I'm going to color in as green, and so on and so forth, right? So there's nothing wrong with that interpretation of a node. But for reasons that will be made a little bit more clear after we talk about the concept of resistance in a couple of days, what I'm going to do is I'm actually going to kind of stretch those nodes out a little bit, okay? So this is the way that I actually prefer to identify my nodes in a circuit. I would start at one end of a circuit element, and I'm just going to follow the lines until I hit another circuit element. So this whole red elbow thing here, we're going to consider to be actually a node. So instead of a single point of interconnection, it's anywhere along that path that connects element A to element B, we are going to consider a node, okay? And I'm going to do the same thing. So starting from element B, I can go to the right some, then I hit this little branching point. I can go down and hit element C. I can come back up and then go to the right and then down to hit element D. And so this is another node. And pretty similarly, on the bottom, I can start at the bottom of A, then go across and up to C, across and up to D like so. And this is yet another node. So anywhere along those paths that connect the circuit elements, we're going to consider that all parts of the node. And like I said, I'll explain why we get to do that in much greater detail after we talk about resistance. Okay. So this particular network then contains three different node points, right? So we might call this node 1, this guy node 2, this guy node 3, or we might say we've got our red node, our blue node, and our green node. However we choose to label them is perfectly fine. I very much like to use different colors to identify nodes. And the reason why I like to use different colors is because they help me to identify whether circuit elements are connected in series or whether they're connected in parallel. So I'm going to explain those two types of connections here for you guys, okay? So if we look at the red node, that's going to be an example of a series connection, okay? So we're going to start with a very simplistic definition for a series connection. And then as we learn more about how elements behave, we're going to update these definitions throughout the class, okay? So our definition for a series connection is going to start as a connection between two, and I'm going to underline it because right now I mean exactly just two circuit elements with no branching paths. So the only one of our nodes that satisfies this definition is the red node at the top left, right? So we can see that there is a connection between elements A and B, and there is no branching off that would allow connection to another element. Contrast that with our blue node, right? So there is a connection between elements B and C, but because it branches off and also touches element D, that can't be a series connection. Same thing on the bottom. A and C are connected, but it branches off to touch D, or D and C are connected, but it branches off to touch A, or A and D are connected, but it branches off to touch C. Any way you slice it, A, C, and D can't be connected in series because there's a branch towards another element, okay? So for right now, a series connection is just two elements connected together and there is no branch towards anything else, okay? A parallel connection. So I put one too many R's there. My apologies. Is going to be a connection between two or more circuit elements where all sets of terminals are shared. And I want to explain briefly what I mean by shared here. And this is where colors are really, really helpful. Okay. So we can see for elements C and D that their top terminals are both connected or shared by that blue node on the top right. And their bottom terminals are both connected or shared by that green node on the bottom, right? So essentially, whenever I see two circuit elements and they're touching the same colors, they are in parallel with each other, okay? So C and D are the only parallel elements in this particular network, right? So B, C, and D all touch blue, but only C and D also share the green node, right? So in order for B to also be in parallel, we would need to have node 1 connected to node 3 through a short circuit or something like that. Okay. So how would you guys describe the connection between elements A and C? Is it a series connection? Is it a parallel connection? Or is it neither? So I hear a lot of you guys saying parallel. You are mistaken. For it to be a parallel connection between A and C, they would have to share not only the green node, which they do, they would also have to share either the blue node or the red node. They don't, because blue and red are not the same color, right? So only C and D are in parallel in this circuit. I literally said that like a minute ago, okay? So this is something that I think the 120 series doesn't do quite enough of a good job explaining. The overwhelming majority of the time, we are not going to have elements that are connected in series and they're not going to be connected in parallel, and that's perfectly okay. None of the above is a perfectly valid option for how these guys are connected, okay? What we're going to learn in this class is techniques and tricks through simplifying circuits to make things appear in series and parallel and stuff like that so that we can make our analysis easier, okay? But for what we're dealing with right now, where we have only generic circuit elements to where we don't know what they are, we can't perform any combinations or anything like that because we don't know if we're allowed to, okay? So for this particular system, A and B are in series, C and D are in parallel, and every other connection is neither series nor parallel, okay? So I want us to look at another example problem and get a little bit of practice on this. So I'm going to go jump to my second page if it will let me. Being dumb, so I guess I'll just scroll like that. And I'm going to put an example network up for you guys. So let's say that we have a network that looks something like this. So I want us to answer the following few questions, okay? Because I'm going to reuse this in a few minutes when we talk about other things, I'm going to be lazy and make a copy of it. We'll get to that bit in a little bit. All right. So these are the questions that I want you guys to answer. A, how many nodes does this network contain? So take a moment, try to sort that out. And then when somebody tells me the correct answer, I'll go through and I'll identify them for anybody who's struggling. That 5, exactly right. Okay. So to identify these 5 nodes, I'm going to do exactly what I showed you guys earlier. I'm going to start on element A, and I'm just going to go up and keep going until I hit another element. And once I've exhausted all of the different branching paths, I'm done. So for this guy right here, there are no branching paths, so I finished. Now I'm going to start on the other side of B. When I hit this node point, I can go down and to the left to touch element C. I can go straight down to touch D, down and to the right to touch F, and straight to the right to touch E. That's another node. Coming on the right-hand side of element E, I just go until I hit element H. That is a third node. Starting from the bottom of A, I can go diagonally up and hit C. I can go to the right and then up and hit D. I can continue on to the right and hit G. So that is a fourth node. And then lastly, starting from the right-hand side of G, I can go diagonally up and to the left to hit F and straight up to hit H. So that is 1, 2, 3, 4, 5 nodes, right? So here's node 1, 2, 3, 4, and 5. So thank you for that, Zach. So the next question that I want you guys to answer is, which pairs of elements are connected in series? So recall that the series connection is only between exactly 2 elements. So that's why I'm specifically saying element pairs. Just going to be groups of 2 elements. Yes, sir. So A and B are connected in series, absolutely, because that red node at the top left, which I've identified as 1, is just touching those 2 nodes, or touching those 2 elements with no branching paths. So that's absolutely correct. And E and H are in series for the exact same reason. So thank you for that. So we have A and B, as well as E and H. Lastly, I want you guys to identify which of the elements are connected in parallel. Yes, sir. So C and D are in parallel because they both touch the blue node and they both touch the purple node, okay? Now, F isn't in parallel with those guys because F touches blue, but it also touches orange, right? And orange isn't purple, so they're not good to go. G isn't in parallel with any of the ones that you've mentioned because it's between purple and orange, right? So the only 2 that are between a shared set of nodes are actually C and D. Okay? C and D are the only parallel connection in this particular network. All right. So let's go back to that first page And let's talk, don't know why this isn't just allowing me to go back, but whatever. Let's talk about a few more things here, okay? So whenever we have a network like this, where we have formed closed paths, we have what's called a circuit, okay? So we are going to define a circuit to be any network that contains at least one closed path. So what I mean by a closed path might be if we started at the green node, went up through element A, across and to the right through element B, and then down through element C, we're back at that green node. So that forms one closed path. Another closed path might be, again, starting from the green node on the bottom, going up through A, to the right through B, and then to the right and down through D, and then we're once again back at that green node, okay? So we're going to call these closed combinations of circuit elements and nodes loops. Okay. So if I scroll up here, how many loops do you guys believe this circuit contains? So I hear somebody saying 2. I disagree. I believe that there are 3 loops. So let me explain. So we have the loop that I described first. So starting at the green node and then coming back around to the green node, like so. So that would be our first loop. We have another loop here, starting from the green node up through C, down through D, that I didn't talk about earlier. And then lastly, we have one around the perimeter of the circuit, which I did describe as a closed path earlier. So that would be 3. Okay. So there are 3 different closed paths for this particular circuit. Okay. Now, being able to identify the total number of loops usually isn't that big of a deal. Okay. Really, after today, we're not going to bother too much with the total number of loops. I just want you guys to be able to think your way through identifying them, because as parts of different types of circuit analysis, we are going to be following currents around loops and things like that. So the last thing that I want to define for today is what's called a mesh. Okay. So a mesh is going to be defined as any loop in a circuit which does not contain a smaller loop. So meshes are essentially just the smallest loops that we could draw for any given circuit. So how many loops are in this circuit? This is where the correct answer is 2, right? So that left-hand window or little box is one mesh. The right-hand one that I've identified as loop 2 is a mesh. But the one around the perimeter isn't a mesh because it contains both meshes 1 and 2, or loops 1 and 2. Right? Yes.
So what shape would contain 3 loops for one mesh?
I don't know that there is one. off the top of my head that can contain 3 loops into single mesh. Because if there's a single mesh, then there's only one loop that can happen. Right? So, for example, if I just very generically let's do something, actually, let's not even bother with it. Sorry. Let's look at the previous circuit that we were dealing with and identify loops and meshes there. Okay. Instead of making something up, let's just do exactly what I was already intending to do. So how many meshes do you guys think this particular circuit has? 4, right? So let me write that question down really quickly. So D for this guy would be, how many meshes does this circuit contain? And I think we can all see that it's 4 pretty easily, but just in case we can't, I will go ahead and identify them. So we've got a triangular mesh right here that I'm going to call 1, a triangular mesh down here that I'm going to call 2, a triangular mesh right here that I'm going to call 3, and then a triangular mesh right here that I'm going to call 4, right? Those are the smallest loops that I can make. Now, if I wanted to determine the number of loops in this circuit, which is exactly what my last question for you guys would be, I would typically subdivide these into things so that I have some kind of formulaic approach, right? So I might first start with how many one mesh loops there are. And the answer to that is obviously 4. Those are just our meshes, right? Well, how many different 2 mesh loops could we make? So somebody said 3. So let's check really quickly, okay? So this guy right here, so this loop containing meshes 1 and 2 is a 2 mesh loop, right? This guy right here containing meshes 3 and 4 is another 2 mesh loop. But I also have a 2 mesh loop right here containing 2 and 3. Are there any other 2 mesh loops that I might be able to form? So I don't think so personally. So students in the past quarters have said something about like maybe meshes 1 and 4 could be combined into a 2 mesh loop, but I disagree with that because you would have to close mesh 1 and mesh 4 to add those 2 guys together. So that's not really a 2 mesh loop. That's just 2 meshes that you're trying to force together. It's not encompassing anything, right? So what I mean by that specifically, let me erase some of this because it's getting real busy. Is if I had to do a path like this to try to add meshes 1 and 4 together, I wind up closing mesh 4 around that path and then closing mesh 1. So that's not really a 2 mesh loop. That's just 2 1 mesh loops that I'm trying to force and it doesn't really work out. So wanted to make that clear as to what the difference there was. So I agree with whoever said that there was 3 two mesh loops. How many 3 mesh loops are there? Just 2, I believe. So that might be something like this guy containing meshes 1, 2, and 3. And this guy containing meshes 2, 3, and 4. So we couldn't do something like 1, 3, and 4 for the exact same reason we couldn't do 1 and 4 earlier. We wind up closing that path. So we're not really encompassing the combination of the loops. So I think there's only these 2 3 mesh loops. And then lastly, how many 4 mesh loops would we have? Well, that would just be 1 around the perimeter of the circuit as a whole. Okay. So adding all of those together, I believe that adds up to 10 total loops in this particular circuit. All right, so does anybody have any questions about anything that we've covered for today? So we largely just went over a bunch of definitions, which are going to be building blocks of the analysis and all of that kind of stuff that we're going to start doing here pretty soon. If anybody has any questions, I'd be more than happy to answer them. If not, I'd like for you guys to work on your in-class assignments, which is just covering this material that we just talked about. And then when you've finished with that, please turn it in up here and you're free to head out a little early. Yes, sir. Try. So all in-class assignments are participation grades. So they are not graded for completeness or correctness. Just if you're here giving it your best try, you get full credit.